So, today's lecture, that is lecture number 4 of this module, and now we will just categorize and we will see the various type of control that is feasible for the HVDC link. We discussed about the constant current controller and also we discussed the characteristic in the previous lectures. Now, here I will just discuss how the CEA control is accomplished. The CA control, as I said, we have to maintain the gamma minimum angle so that the commutation failure can be avoided, especially in the inverter, because the commutation failure is only possible in the inverter because the rectifier we are having the valve voltage most of the time it is negative. So, the commutation failure may not occur. So, we know this we have to in the CA control we are maintaining this is your commutation voltage of any valve, and if I am writing this for the valve 3 it is a EPA, and this is the zero crossing, and basically we are maintaining this period that is a gamma minimum so that the commutation can be successful even at the during time of after firing or the during time of the firing if U is changing. So, we should land up here and there should be successful of your commutation. So, based on this we are just calculating the angle beta where this inverter is to be fired, and we are calculating at that time what will be the value of U. So, for the known value here U, we can maintaining this we can calculate the B instant, the beta instant, and then we can give the firing pulse. Now, in this condition here you can just write, because here we are talking about the 2-3 valve conduction mode, and this expression we already derived if you remember. Here we are talking that earlier 1 and 2 valves were conducting and 3 is given pulse. So, in that case your valve 1, 2 and 3 are conducting. So, the current which will be basically there will be commutation from 1 to 3, the current earlier it was ID here, now it is going to be taken by the 3 current, and we derived this expression that is a 2L di by dt EBA. Taking the our convention of your this is a sinusoidal that we are taking 0 axis here, this is voltage, and you can calculate the current here, you can integrate here what will be the value. The instant that is a T1 here, it is your this value is your T1 and this value is your T2. We are giving the firing instant here where the valve 3 is going to ignite, and it will ignite because the voltage across this valve is positive, and if the here the ignition is successful, then it is a T1 instant, and then it is going to be off, 1 is going to off, here means 3 is taking complete current of this link. So, the T1 will be basically nothing but if you are measuring from here. So, this is basically nothing but your alpha. So, T1 I can write it is nothing but your alpha divided by omega, because this axis is your omega t. So, this omega t here at this point is alpha. So, it is a T1 instant we can just calculate. Similarly, the T2 instant here it will be the pi minus this angle. So, I can write here the pi minus gamma minimum divided by your omega. So, now we know that at this instant your I3 was 0, and at this instant I3 becomes your ID. So, you can solve this equation here just to integrate from 0 to ID for I3, and this is from T1 to T2 where we already defined here, and if you are just integrating this you are going to get this expression. And finally, we are getting this expression, means we can write our cos beta that we want. From this expression we are getting the cos alpha, and the cos alpha here alpha is basically nothing but your pi minus beta. So, we are going to have this equation, means we are getting your cos gamma minimum minus your this value that is 2 omega L divided by under root 3 EM into your ID. Basically, this value is nothing but your IS3. If you remember, this was the base value earlier, and if you divide here, because that value was under root 3 em divided by 2 omega L. So, it is same we are getting here. Now, this beta basically we are fixed, this value is known at the time of firing, this value is known, L is known, em is measured and ID is also measured. So, we can calculate the beta. Only the problem, once you have a given the beta here, this gamma, because before the firing this gamma here, this ID is assumed as a constant, but it may not so, because that may change during that time. So, this ID is basically replaced by your this ID plus some alpha here. As I said, this ID is now replaced by ID prime. We are adding some small, that is a magnitude of this delta ID, some percentage of this in that equation here, so that that can take care of any change due to the U interval. So, this is basically decided based on the practical condition, how much it is going to change. So, this ID is now going to replace by ID prime, and some percentages is basically depends upon the converter link, what is the distance, etc., everything, and is based on that experience this value is added. Now, another here, as I said, there is a possibility if your inverter which is operating as a constant extinction angle control, due to the some severe voltage dip at the inverter end, this may shift to the constant current control. So, already we defined the characteristic here, this is your alpha minimum, here the CC constant current here, and this is your, this is the CC. So, this is your CA. So, this is your inverter. So, it was operating here. If there is a sudden trip here, you may land up somewhere here, that you should take care. So, we should have a smooth transition from here to here. Then how we manage this, how it is going to be changed here. So, that is here in the event of the sudden system disturbance due to the end this AC and inverter voltage rise or the dip in the DC voltage. So, what will happen if the voltage is going to rise the inverter end, then your ID is going to reduce, or due to some problem here, means there is some voltage dip in that one DC link also, that may cause your current should be here is a decrease, and then what happens, this side your controller is saturated, current controller is saturated, then it has to be shifted here. So, what we do, we gamma here basically increase it, and then it will be shifted here and the control. So, normally what we do, first we change here gamma minimum, increase the gamma minimum, and then we shift to constant current controller, and this will be operating. We will see again, even for maintaining the constant power, how this characteristic from here to here and here to here is going to change. Suppose right now what will happen in this condition, this is your operating point, and your power characteristic if you are drawing, it will be this characteristic. Why? Because we know this PD is nothing but your VD into ID in per unit. This is your ID, this is your VD. So, the power characteristic will be for a given here, this intersection will be operation, and the power which will be flowing in the link will be this value, this characteristic, means this current multiplied by this voltage. So, this is your voltage and this is the current here ID here, this one is the VD. And now, we will see if suppose it is operating here in this mode due to the certain problem. Now, you can see if suppose this has gone down. Now, the power is also changed in the link. So, we will see how it is going to shift, how we can change, so that we can maintain the constant power control in the HVDC link, in this link. We will see in the few next slides. Before this, this is the complete. If you will see this figure, here we are having the rectifier, this is the rectifier, this is your inverter, and this is your link. It has a resistance, it has a smoothing reactance both side, or you can have a half, so it is no problem. So, this is your rectifier and this is your inverter. Here you see the firing pulse is generated to fire it. Here also in the inverter side we are giving the firing pulse to ignite it here. We are having extra here, I have written the TCC. This is the transformer tap changer control. Till now I was discussing here, because this is only alpha control in the rectifier. but to achieve the VD call here, as I said, here this characteristic will go here, and this will be basically the constant voltage, and then finally here. This characteristic is modified when the inverter voltage has gone suddenly low, very low. So, this controller from here the characteristic will be totally shifted here, and in this case we are operating at very less power in the circuit. We cannot maintain if the voltage has gone down suddenly very low, your converter station will be stressed highly. So, that is why we reduce power, and finally we operate here in this zone, and this is called VD call, means voltage dependent current order limiter. Means the voltage has gone down, your current order is changed, and finally we operate in this zone. To take care of this, we measure the voltage of the link. You see here, thus we measure here the voltage, and we know how much power is flowing in the, how much power you have set it. So, this divided by this means you are getting some current. If voltage has gone down very less, this current value will increase. Once this value will increase, based on that your video call will see where you are going to operate, means this will limit your ID current, because this current is going to decide here if it is hitting this value or this in between or less, based on it will be decided. And then your ID is set, and this I naught is set, whether you want to set this here or you want to set here. So, this will be giving information, this reference current will be decided. If it is video call is not constraining here, it will be your actual ID if it in this zone, otherwise it will set, and then finally we have to change the firing angle and we have to operate this zone. So, this VD call here, that limiter is also added. Now, you can see there is another signal coming from outside, basically that is nothing but it is based on the power how much you are setting. If you want to increase manually power, how much to increase, another here you have to add it here, because this P naught and other power is coming here all the way. This P naught basically coming here, VD only coming from here. So, this P naught basically how much you are setting in this, that is deciding your current. So, this reference is decided, and then it is measuring the current here, and if there is some difference, then your here the current control amplifier is there, it is amplifying the signal, and then firing control angle is here, is calculated, and then it is coming here all the way. So, this is basically your control characteristic of your rectifier side, it is taking care. However, this, as I said, if the voltage is changing very suddenly, because we have the limitation of alpha, because we have the alpha minimum as well here, maybe 1 or 2 or 5 degree, and also we do not want operate alpha at the larger, because it require more reactive power. So, what happens, this will be here, it will be set, and this will be checking what is your reference set of alpha and what is the current alpha. If there is some mismatch, then it will start, this type changer will be there, and it will be trying to change your converter station, a rectifier, and it will be the typing will be changed to control again the current will be this, because this alpha is decided by current, and this is also changing the voltage, which is the current is there. So, there is a complete impact here, and finally the current will be maintained in this side. Reverse is also true here, you can say the VD call here also we need, and then it is coming all the way here, and finally we are here the gamma is beta is calculated, and we are firing this inverter based on the gamma minimum angle control, CA control, and the beta is coming here. Here this TC, this control is basically the so many aspects are there, because this side, this fellow is maintaining the voltage, because the inverter end is the voltage control, this is your current control. So, it is current is taking here when deciding, here also no doubt the current is taken for this controlling, because the current also require, but this we are comparing the voltage plus the drop in this circuit here, how much this, because this voltage and this voltage here drop, and then finally if there is any change with this voltage, then we are changing here. This video is the reference, how much voltage we are going, then suddenly you are changing here. So, it is your transformer type, inverter side it is changed. So, this is complete control essentially both rectifier as well as the inverter side. Now, let us see, I think since we are starting here, it is let us see the power control first, then we will see how this, even though your converter whole HVDC link, when there was no power, how it is going to start it and how we can down it, because it is not possible suddenly you can just start full current and you can just load this HVDC link. So, to understand this constant power control, again I will come here and you see your actual operating power. I can just remove here. This is your P1 point, I can say here. You can see when rectifier is on CC control, P1 is the original operating point here, that is a control of this one, because this is your rectifier CC, this is your CA and this is your operating point. When the inverter is operating in the CEC mode, the power in the link becomes P2, means what happens here, this is your P2, because due to certain problem here, there is some voltage has gone down and now it is operating in the CC and this is operating in the voltage control. So, this is your P2, and again if you draw this here, this characteristic, this will be like this. Now, what happens, you can say this power is less than this power, because this is more, VD and ID both more. Here ID is also less and the VD is also less. Now, to maintain the constant power, there is a two option that we can increase the current, this one current here, so that we can have, because you know what happens here, if this is your here, we can just increase here and this intersection can be there. So, one option that we can increase this current or we can increase this current. First, see, we want to increase this current order of your rectifier end. So, the first the current of the inverter is increases, so that operating point is P3. Here it is not inverter, it is basically the rectifier end, because here we are increasing inverter, here is the rectifier, just you can correct it, here the order of rectifier is increased, so that operating point is P3. See this graph basically, already I have drawn here and you can see here what happens, this your P1 here, it was your the point of operation as I said. Now, due to the change here, this is your inverter is taking the constant current here, this is your CC, this is your CEA and this was the CC of inverter, this was a CC for your rectifier. Now, you can say the power is decreased. Now, what we do, we want that this power, this characteristic, this CC here should shift from here to here. If you are shifting this axis, it will cut somewhere, it will be that is point is your here, because this is the voltage and this you are shifting here. In this case, the power is P3 and that is again you are maintaining. So, the what happens, it is better that we are basically increasing this characteristic, the current order C here, to get the same power. This is the now new current and this will be our operating point. So, what we do, if the power has gone down, then we try to increase the current order CC setting, that is the ID here, which was the reference, it is increased, so that we can maintain here with the same power. There is also there was option, you are operating here, this is your here in this inverter side, this can be increased. If you are increasing from here, you see what happens, you are having another intersection at this point, because how you can increase, you can just increase with this axis, because this is your beta control, you are just doing the beta control here, you are coming here and then you are getting the P4 intersection, it will be you set your operating point suddenly, because whenever your inverter characteristic and the rectifier characteristic are intersecting each other, that will be your operating point. So, it will be intersecting here, and now you can say in this case you are increasing the current order, but at the same time here the voltage is also reduced and the power is also less, because this power is very less than even your P3 here this P0 value. So, it is advisable that it is better to shift this characteristic, means current order of the rectifier, so that we can get the suitable operating point P3 and we can maintain the power, that is the constant power. So, whenever the power is changed, because the power controllers are there, the power is basically ID, which is decided, why ID is calculated if the power setting your constant power operation mode, because your reference ID is changed now and it has become this value. So, your controller will take action and ID reference value is changed, and now we are operating here rather than here. Now, another concern here, that is how we can start or stop our link, how we can go ahead with this. So, in general, this HVDC link can be started by the two methods. One is called using the long pulse gate pulse, that is if you are giving the gate pulse of valve for 120 degree or you are giving 60 degree. So, if you are talking about the short pulse, then it is 60 degree, and if you are talking long pulse, it is 120 degree. Why it is 120, why 60? Because if you will see, if you are giving 60 degree, after that, even though that is required pulse should be there, it is not there, then you will get the valve will be not on. It depends on what is the voltage across this. So, if you are talking about the long gate firing pulses, it is very simple, because here what you have to do, you have to deblock the inverter around this 90 degree. What does it mean? We are having, this is your, just I will explain with this example. This is your rectifier, this is your inverter. Let us suppose it is here the monopolar operation, whatever you can see. Now, what we do here, it is said deblock, means earlier it was not doing anything. Now, we are just giving the firing pulse to this, and especially we are maintaining the gamma is 90 degree. If you are giving the 90 approximately 90 degree, what will happen? The voltage across this will be 0. You are just turning deblocking here, you are giving here 90 degree, and it will be on. Now, in this case here, now you have to deblock this rectifier and give alpha is 85 degree. We are not giving 90 degree because there will be some U. Once this is on, there is no current is flowing here. So, U is not applicable at all, because it is simply it is a VDO cos gamma. So, the gamma is 90, it is VD is 0. Now, if you are going to give here 90 degree, what happens? Due to U, even this voltage may be negative. So, what we do, we try to give some positive voltage, we try to ignite somewhere around 85 degree or so, and still this voltage is very, very small. So, now you are just starting this as a valve. Now, your voltage is here, and now the current will start flowing, a small amount of current will flow, because this is 0, this is very small voltage, approximately 0, some current will be flow. Now, what we do, we then increase the voltage. What will happen? We have to decrease this, we have to decrease this slowly and slowly, but again in this case, now the question is that we can increase the current together, we can increase the voltage together, but it is preferable that we have to raise the voltage first, then increase the current, because if you are increasing the voltage, why it is so? It is possible that you can just change this value, keep it this, current will increase. But we do not want this, because what happens, the current once it is flowing, if there is some problem of insulation or anything, there is a huge short circuit will be there. So, we try to increase the voltage and see the line is okay or not, even though a small amount of current is flowing. Once it is sustaining that voltage, if there will be some flash over here and there in the towers and insulators here and there, then you can just check it and then you can stop it again very easily without, because the current was very less. So, what we do, we try to ramp, already here it is, you can see the ramp of voltage by inverter control and current by the rectifier, we have to increase, but what we do, first we increase the voltage to have the minimum current here, means you have to increase the voltage, means ramp, then you have to load this link by maintaining the current. So, basically this is the starting of our DC link is done if you are using the long gate pulse. This 120 will arise long pulse, because here you are starting, at that time there is a huge possibility of the commutation failure, because if the 90 you are using, here there is the voltage across that valve may be negative, because we saw that the voltage, valve voltage here in the inverter operation is most of the time it is negative. So, to avoid this, if it is at 60 you are having 120, this pair will operate. So, there will be no problem. But if you are going for the short gate pulse firing here, So, the current extinction here, as I said, in the inverter operation is a problem because the forward bias is not in the conduction mode in the inverter side. So, the sequence of in this case will be first open the bypass switch at one terminal. Basically what happens, all this here the converters, they are having a bypass valve here, or we are having bypass switch. This is a valve, means what happens if there is any problem, this is basically equipped with this. This is used especially suppose you want to take it out. What happens, suppose you are having another here valve, this is your converter circuit. This is, let us suppose you are having another here, we will explain this more detail. Now, you want to take this bridge out for the maintenance purpose. What happens? Without creating any problem, we want some current should flow like here, then you can take it out. You cannot suddenly here take it out, this valve, then it is a current is 0. And also it is not possible that simply just put it here short circuit and then it will be taking out. Still it is very difficult because there will be huge charge and huge problem will be there. So, either we use here bypass valve or we use bypass switch. Switch means here simply here the opening or closing. In that case, you cannot open and close if the current is flowing. So, what we have to do, we have to create some voltage across this is 0, then only you can close it. Otherwise, huge here sparking will be there. You know, it's just like a circuit breaker. Here, if the voltage is there in between these two, connecting huge spark because the gradient will be there potential, and this will be here, air will be ionized, and there will be spark will be there, it will damage it. So, what in that case we do here, already we use one pair of valve as the bypass valves, because here we are having, you can say this is 1 and this is your 4. If both are conducting here, the voltage across this becomes 0. And once this is there, this current is flowing, at that time you can close it here and then you can open here and the current will be flowing without any problem. So, we use either bypass valves or we use bypass switches. If you are using this concept, then the switches are used. If you are using this valves, then valves are also used, but this will increase the extra cost because you are maintaining thyristors are more expensive than a switch, because in this case also you may require switches. So, here the open the bypass switch at one terminal means this is a switch, because earlier it was open, means now you have to open it. Now, it is ready to conduct the current. So, deblock the terminal means terminal was blocked. Now, you have to give block means just there is no firing pulse, all the gate pulses are blocked. Now, you are start giving the gate pulses to the valves. So, deblock the terminal and load to the minimum current in the rectifier mode. Now, you have to use here, suppose you are using this one. So, you have to operate this as a rectifier. This is switch is closed still, we are not opening this one. This is still there, and then the current you have to flow here. So, one which is you as a deblocking, you operate this as a rectifier. If you are using this, you can use this as a rectifier. So, if you are taking this as a first one, let us see. So, what we did, we opened this. This was already closed, and we are talking here only the monopolar operation for simplicity. Now, you are just deblocking this, means you start giving the pulses. Now, it will be conducting. The pattern again it will be the follows at the 6112, this pattern always symmetricity will be there. So, we are generating some voltage, small voltage here, and the current will start flowing here. So, this current is very minimum current. So, what we do now, this switch we have to open, and the same time we have to deblock first. Deblock and then open this switch, this current will start flowing here now. Now, bypass the second terminal and the commutate the current by the bypass pair. The start the second terminal also in the rectifier mode, means another one is also in the rectifier mode, means here the voltage here is just opposing in the additive here, because you are connecting in this way. So, this is also additive. So, the current will be flowing even though for the small voltage. Rectifier mode, the inverter terminal is now put into the inverter. Now, you have to change your angle in such a way. If it is a in beginning both are operating as a rectifier, because we do not want to use the inverter in the beginning, because the short gate pulse there is a commutation problem. So, to start with you have to flow the current, and both should operate as a rectifier. It is possible, because the voltage mismatch will be there and the current will be flowing here. Then you have to change the firing angle. This angle, this is, let us suppose you are operating here is a 90 approximately, here also approximately 90. Now, this angle alpha should increase, means the beta should reduce, and this should reduce here, and this rectifier, this is inverter. And this is basically the procedure, and finally it will be taking complete current and the voltage. So, once you have started, this is rectifier, one is inverter. Now, you have to increase the voltage, and then you can just load this link into your HVDC. Normally what happens here, while the raging, the power increase is not beyond the 2 to 10 per unit per second. This is possible that suddenly you can just here from 90 you can go for 0. It is not possible, because if you are doing this huge current, and even the smoothing reactors are there, huge voltage drop across the line will be there. Di by dt now it is through the inductor will be there, and that is a very dangerous for the HVDC link. So, it is advisable that you should operate to 2 to 10 per unit power, rate of change basically, it is not power, rate of change per second. So, already I discussed this one. Now, other control objectives of this whole HVDC link, that we can control the frequency up to limited extent. We can control the reactive power again up to limited extent. We can control the tie line power with the full power, it is up to you. You can control, you can use this HVDC link for emergency control as well, and we can also use for the subsynchronous resonance control. To control the frequency here, we know that the system frequency, if it is AC system, the frequency is directly related with your load generation balanced. If your generation is more, load is less, frequency will rise. If your generation is less and load is more, then frequency will fall, because it will utilize your rotating energy, that is a kinetic energy in the system. But it is also possible if the two areas are there and they are connected with the HVDC link. So, you can feed from one area power to another area power to change the frequency of that area, as we can utilize this controller. But if it is a complete in the integrated system, means then it is not possible. So, the frequency control is only possible if the two AC system, this is AC system, here we are having another AC system, or you can say area, and now it is connected with here HVDC link, then you can control the frequency of any area by here power flowing in this area or taken from this area. But if you are having here AC line and you are having the DC here in between somewhere, you cannot do the frequency control at all, because that is then always it is your this generators and your demand will set your the frequency. So, with this, if you are having the here some connection, then you can inject more power into the system, or you can withdraw more power, means basically what you are doing, you are, this bus is just like a generation or load bus, and therefore you can control the frequency of either this area or this area. So, only it is possible, especially like we are having back to back connection, then we can flow more. But even though let us suppose you are having a DC here, DC link, and you are having another AC link here. In this case also you AC line is there. So, if you are controlling the power here in this, it will go back here to maintain the frequency of the system. So, that is why here the frequency control I am saying with the help of HVDC link is a limited application. It is only true if the two different systems are connected by the DC. If this is also DC, it is possible. But if it is connected in the AC system, inside your DC is built, you cannot control the system frequency at all, because frequency is related with your generation and power. So, this is your frequency control. Now another I can discuss here your reactive power control. Reactive power control is basically in this fashion. You know, the converters are consuming reactive power. Both inverter as well as the rectifier, they require huge reactive power, and here we are having some capacitor banks and other things. In the reactive power control, I mean to say that here with the help of firing angle, if let us suppose the voltage of this bus is going to be very high, you can fire this alpha is very large value, reactive power requirement of this converter is going to be more. So it can consume more reactive power from here. But it is not advisable. We never do unless until really you are in the emergency. Because if you are changing this alpha, then here also gamma should be changed accordingly to maintain the power here. And then it will be absorbing the reactive power from the system more and more. So you can do this reactive power control up to the limited extent, and especially in the really critical conditions when your system maybe let's suppose voltage stability conditions and other things arising, then you can utilize, but still in normal practice we never do the reactive power control with the HVDC link. So next control possible is the tie line power control. That's very simple and really it is very useful, especially we do when we are talking about the back-to-back control. Basically this is nothing but the two areas. Here again we are having the HVDC link here. It may be the long distance transmission HVDC line, or it may be short distance, that is the back-to-back connection, means they are both converter and inverter stations are very near to each other, and only our intention is to control power from one region to another region or from here to here, then it is possible. So you can say the tie line power here we can control from this one, from one area to an area. And here, even though you can say the tie line power control, I want to say there is a possibility this area is having the deficit or you have a surplus of power, but if you are setting the power here, reference here your P, it will be still injecting the power there. Means you can when the force it here, let's suppose it has a this P is higher in this zone and this is also injecting this, means frequency of this system will go up. So it depends normally based on this here, this area and this area agreement, if the power is now is the more here, that can be coming this side or this side. So we can control very effectively this your tie line power in the two area. Even though this area is connected by AC line some other point, but still we want to control somewhere here as well, because this power, this line may be very weak sometimes or very small voltage connection. Here we require long distance power as well. So the tie line power control, no doubt this in HVDC is one of the major objectives. That's if you are having back-to-back connection, means it is one area, another area they are controlling to each other. Tie line means the two areas are connected. So the two area here I can say, and especially it is a back-to-back connection. Now another is your emergency control. Emergency control, basically what happens, sometimes here this is a set for the certain power, even though inside is not only the area, it is, let's suppose inside you are having this HVDC control, your system, some of the lines are tripping and this is set at certain power, let's suppose even though 1500, let's suppose it is rating is there. There is a possibility that we can load this line even though more than this 1500 for few minutes. Because if a line is, some line is let's suppose tripped, what happens, one line tripping may give your cascade tripping due to the overloading of other lines. Because this power it's not going to change even though tripping of any other lines here, because here this is operating as a constant power mode. So this will be flowing as it is. But if there is some lines are going to overload, momentarily we can increase this power for a few minutes and then we can just synchronize or we can reduce our power levels, generation and load balance in such a way that our no line should be overloaded even the outage of few lines. So in the emergency we can operate it this. Now at that time this 1500 setting is no more required. We want to maintain the stability of the grid first, and then therefore we can do it here. And this is very, very useful, especially in the emergency conditions. It is working very effectively. So the emergency control means the control which is, it is used for some other purpose. It was used to flow huge amount of power from here or here to here. But during the disturbance, abnormal conditions, the objective is changed to stabilize both of the system or the same system because we can alleviate the overloading or operating conditions in the normal limit. So that is your emergency control. Another here is your SSR control. It can do SSR, again I was explaining even though in the previous lecture, that this phenomena normally happens when you are having this your power plant, thermal power plants. You are having the huge turbines like your high pressure, intermediate pressure and low pressure turbines, and then your generator is connected. Then you are having so many critical frequencies. So in this case, let's suppose this is your turbine, high pressure turbine that is connected with your IP, and then we are having LP, this low pressure turbine, and then we are having your synchronous generator, and now here we are having some HVDC link. What happens if you are putting this one here? This may, if the frequency which was entering here from another area, it will not go inside because due to the DC. Here means, of course, you are having this is an inverter here, means if it is entering some frequency which is in the system, it will block here. So it will even though control sometimes that it will not going inside to the generator winding, that current harmonics, and therefore there will be no SSR problem. You know the SSR problem is a subsynchronous, it is called, means subsynchronous is your 50 hertz, means that frequency is less than 50 hertz. But I am sure people have not heard the supersynchronous resonance, because they are designed in such a way. Here the frequency of the critical frequency always less than 50 hertz. So even though you are having the higher frequencies here, those are entering here, that will be not having the this torsional oscillation concept. So that is, we never bother about the supersynchronous. Means if frequency is more than 50 hertz, that is a multiple of frequency intra-harmonics and your integer harmonics. So that will not affect at all, because if less than this will be entering here, then we make these critical frequency may synchronize and maybe matches, and then huge torsional oscillation or torsional torque will be developed, and this shaft may be broken. So this can also do if it is used in this way in some specific purpose. It is not necessary that we can use like this, because we may have some AC lines also. So this may enter in this way. Or if you are having the AC line and the DC line, and then you are having some filters here for those, then it may go down, it may not enter here. So that possibility is there. So if your filters are here, that may go down here due to the HVDC link. But it is not always, because we are using the filters here only for the characteristic harmonics. So this 50 hertz, less than that we are not bothering at all. So it will go inside. So this is your SSR control that it can do up to certain extent if it is properly designed. Now the major question here, that suppose you want to take out the bridge or you are putting in the service, and it is a very common phenomena. If your sum of the valve is damaged, that should be taken away, and then you have to repair it. It is not possible that inside you can do it properly if it is energized. Means taken away means you can bypass this, and then you can do whatever you want to do here. Maybe there is a failure of the coolings of these thyristors or GDOs, then you have to repair. So in all the maintenance purposes, etc., you have to isolate this your bridge, and then you have to take care. As I said, it is not so easily that you can open the switch and take it out and close this switch, current will be flowing here, because it will introduce huge harmonics in both AC side and the DC side, and it may damage your even the bridge circuit as well. So we adopt very procedural way here. As I explained, there is a possibility that we can have here a valve that is called the bypass valve, and or we can have only the here switches, then we have to use one of the here circuit to use as a bypass valve. You can see this is a conducting, means it is a short circuit. So if you are conducting anyhow 2 and 5 together, then it will be short circuit, the same purpose. Similarly is there. So either you are using this here bypass valve, or you can use the pair of here the valves in the same leg. So both options are there. Only in that case what happens, you have to wait a larger time here if you are using this one, because you don't know when you are going to decide it. So let's suppose you are operating at, let's suppose your 3 and 2 and 3 are operating, and you want to make this as a, or this bridge as a bypass pair. So then 2 3, then 3 4, 4 5, 6 1, then 1 is coming here, then you can then wait for 3, then go for 2, then 3, then 4 will be coming, then it will be short circuited. Means it will require sometimes maybe from 120 degree to 180 degree. Means what is the instant of decision? It depends upon, you can also choose this pair, you can also choose this pair. So first we will see if we are having a bypass valve, how it is going to be operated, so that the current here which was flowing here earlier through these valves, either this or another will be here, means one from top, one from below, and then we are having this ID current here. To see this, now let us see the rectifier circuit, and I am taking the same configuration, 6 pulse bridge converter. Here I say that the 6 1 is conducting, the pair of valves 6 1 from here. Now then 2 is given fired, and now it is a conducting here. You can see this is a rectifier we are talking now. This is 2 is fired here. Now the possibility that here we can give the command to 3 at this point. You see it here. 6 1 2 is the commutation is between your 6 and 2 is taking place, because here we are giving the firing pulse to here we can give, because you can see the voltage is going to be positive. Now this 6 1 2 due to the U period, and now here this is a conducting your portion, this EA this. Now 1 2 is, let's suppose, is conducting. Now we have decided to bypass it, means we want to take. So what happened, we have to give the firing pulse to 7, means this is your, to understand this is your 6 pulse bridge converter. Here we are using this valve, and this is your ID, this is your 7, this 1 4 3 5 6 2. Now once your 1 and 2 are conducting, what will be the voltage here? 1 it is EA, 2 it is EC. Voltage across this should be positive to get it fired. Means voltage we require here, ECA should be positive. If it is negative, it will not conduct. Now you can see what happens. Here 1 and 2 are conducting. You can see what is the voltage. This is your C, this is here, it is negative, because it is CA, this minus this is still negative. So if when you are giving the pulse here, it will not conduct. So what you have to do? You have to wait. Now you can see after this, now this was the D point, was the point where 3 was given a pulse. In our sequence, it was your 6 1, then 1 2, now it is conducting, now 3 is going to come. So what we will do, we will block this pulse. We don't want that this should conduct. If this is conducting, here again this voltage across this will be negative. So what will happen here is, at this point the D was coming, means your valve 3 was coming, we stop the block gate pulse of this one. Then this 1 and 2 is continue to conduct. Now you can see at the point here, when EC and EA is going to be this, means at this point ECA is 0, now it is going to be positive this point onwards. So we waited till here, now 7 we gave the pulse, and once we are giving the pulse it will conduct. Now before that the current was flowing here, and it was going like this. through this winding it was going. Means here it was your this is not conducting here, and your voltages were there. This is EA, here is EC, and this was your EB. Now what is happening? This current which was flowing here, now there is going to be a commutation between 1 and 7, 2 and 7. Because this current is now basically, in fact, we are having the commutation between 2 and 7. Because the current which was flowing here, ID, is now, earlier it was flowing here, now it is going to be shifted here. And it will take some period, some time, when it will be basically the complete transfer of the current from here to here, it will take place. And this current will become, this side it will be 0. You can see here, this is I1 here when we are giving the pulse, this I1 is going to decrease, I2 here 0, here this is I2 is also going to decrease, and your this current I7 which we gave the pulse, it is going to take care and it is going to be ID. Once it is there, ID is taking full current. Now what happens? This is a short circuit. This is the short circuit here, means this current is completely taken. Now you can open this one without any problem. You can take it out, this one. Now here there is no switch. So what we do, we put the switch here. This is your switch. This is a switch. Here we are having a switch here. So what happens? Earlier it was closed and the current was flowing now here. Now this voltage is 0. Now we can connect this. This is both are short circuit. Now you can open here, the current will be totally diverted because the voltage across this is 0. So you can open this now and you can take it complete bridge together, means even including this. You can see here how the voltage is going to change. During this period, there is some voltage, the positive side here, this and this is going to be same. Because the voltage across is 0, what is happening? This C and this EA is going to be 0. This voltage here as here means this voltage is nothing but the addition of these two voltages, it is your EB by 2 minus. We already proved here this voltage EA plus EC by 2 will be minus EB by 2. You can see this is here EB by 2 minus. And this will be the same, this will be the same, and that's why the output voltage is 0. So you can say output voltage, it was following here, it is continuing here, it was coming all the way here. Once whenever we are giving this here, it is following this EB by 2 till the commutation is finished, and then it will be 0. And then finally it is going to be this. Because once this current is 0 here, this voltage will be 0. And this is the circuit. So basically on the next turn and next lecture, we will see how this current is going to change from here and there, and then we will see how it is different in the inverter circuit once we are using the bypass valve. Then we will see if we are going to take this pair, how we are going to take out again using, if we are not having this bypass valve, we are having this only switches, we are using one pair, what will be the sequence and when we can take it out in this one. So this is basically the de-energization. Then we will talk about the energization, reverse process. We have to put in again into the service after repair, then what will be the sequence and the procedure will be followed. So with this I can stop it here, and in the next lecture we will see the complete again the derivation of the current commutation here and also the inverter de-energization. Then we will see the energization, then this control aspect will be the closed. Okay, thank you.